Good afternoon, friends. Welcome to the 11th technical lecture by IIF NCTS. Today's subject is sands and coatings for steel castings. Mr. Panse is our faculty for today. Mr. Panse is a metallurgical graduate from College of Engineering, Pune. During his career of more than 2 decades in steel foundry industry, he has worked in reputed foundries such as Bukun's Iron and Steel, Nitin Castings, Galaxy Spectromet, and Titan Alloys. He also has an experience of running his own steel foundry, and he currently works as a consultant for steel foundries in India. As he is always ahead in sharing his experience and knowledge acquired in his career of more than 4 decades, we will be definitely gaining from listening to him. Now I request Mr. Panse to take over. Thank you.
Thank you, Mr. Soni. Today we are going to discuss the surface finish, coatings and sands for steel casting. For many casting buyers, a smooth uniform surface finish is more than a visual appearance. It is more than a first impression or packing of a product. It gives confidence to the customer that you have taken sufficient care in producing the product. It also saves a lot further work in a foundry in fettling shop, like cleaning, finishing or machining for the intended final use. It is the most desired characteristic, is predictor of a performance of the minor unevenness or surface finish characteristics. The irregularities act as nucleation sites and affect the mechanical properties, especially the strength, fatigue, etc. These irregularities act as the nucleation sites and also affect the corrosion properties of stainless steel castings. Attaining good surface finish in steel casting poses problem as the pouring temperatures are very high, the metal is reactive, and since the yield is very low, large number of feeder, chills, paddings are required, and in removing and finishing them, the original texture of the casting gets distorted. Also, the typical phenomena of reaction with the mold is caused by the oxidation of the iron particles, which does not happen in CI or HG casting as the carbon itself is very high, and also the carbon in the sand and painting helps, and that's why you get a better finish in HG and CI casting compared to steel castings. Nowadays, surface finish is become an integral part of the quality specifications. Customer will specify that so much RMS value of the texture is required. It also affects the performance. Say by example, pumps and valves, the inside portion is rough. The velocity of the fluids and the product will get affected. Also, mainly casting forms a small part of a total equipment, and the total equipment is of a different look. You cannot have a bad part in a total equipment which will get highlighted. Also, the surface finish of stainless steel casting is very important for corrosion characteristics. To avoid the increase the corrosion resistance, even in stainless steel casting, you are doing acid treatment on the surface. So even the small unevenness can reduce the corrosion resistance of the product. The surface roughness of a casting influence basically by the sand you use and the molding process you use, the pouring temperatures, the hydrostatic pressure in the pouring. The principal aspect which decides the surface finish of the casting is the sand you use and the molding method you use. The major sand used is silica sand because of its availability, and it meets most of the requirements. In India, you get very easily more than 98% pure SiO2. It has small quantities of ilmenite, that is FeTO3 and magnesite, but 98% purity is good enough. And the Allahabad sand, which is on the banks of Ganges, is supposed to be one of the best sands in the world. As per NMI survey in 2015, the the total silica sand reserves in the country are 4,000 million tons, out of which around 735 million tons is suitable for foundry use. That is sufficient stock of silica sand is available. Normally, the surface finish specifications like ASTM 802 or MSS 55 for walls specify various characteristics like surface texture, non-metallic inclusion, gas porosity, fusion, expansion, inserts, metal cutting marks, grinding marks, etc., etc. But we are going to consider this basic surface texture of a casting. As these other defects, there are other things also we can contribute. For example, gas porosity can come because of the basic gas in the metal itself, gas generated by the molding material, gas picked up during pouring in the running system, etc., etc. So we'll concentrate basically on the basic texture of the casting and how we should get a good texture. The casting texture or surface finish is characterized and classified by RMS values. They are classified on a standard strata comparator from 20 to over 900. For best of sand, that is shell molding or no-bake and very fine sand, you can try for around 150, 200. For most of the castings, you will get around 4 to 500. You should try and see that you don't touch 900 or cross it. The surface finish you get is mainly dependent on the fineness of the sand. The finer of the sand, the better texture you will get. However, when you are pouring heavier castings, the fine sand will get fused and sand fused layer will be there. So you have to use coarser sand and the original texture, that is RMS value, will be of a higher side. So we'll see what are the basic requirements of sand grains for using as a molding material so that you get a better surface finish. Naturally, the best characteristics is mechanical stability of the sand. See, sand is mined, then transported, then it is mixed in the muller or mixer, then it is exerted certain pressures in making a mold, that is ramming or jolting or squeezing or whatever method you use to make a mold. Then again, metal is flowing on it. Then again, you are knocking out the sand. All these mechanical forces applied, the sand grain, basic grain should withstand these pressures and should not disintegrate. Otherwise, more fines will be formed and the shape will be distorted every time. Second most important property required is thermal stability. You are pouring steel casting somewhere around 1500 degrees centigrade. The thermal stability is very important. It should not change its physical and mechanical characteristics when the metal is poured. The third important characteristic is chemical reactivity. When you are pouring a metal in certain type of a mold, if the metal is alkaline and the sand is acidic, like you are pouring manganese steel in a silica lining, the reaction of the metal with the mold is likely to be more excessive and you are likely to get a bad surface. So you should consider the chemical reactivity of the basic sand, considering the temperature of the metal you are pouring and the type of metal, its chemical composition. Then the sand grain should be compatible with the binders. Sand you are mixing with various binders, so it should be compatible so that a good mix of sand is you get. And Naturally, it should be available in abundance, economically and geographically also at various places. That's why silica sand satisfies most of these needs, and hence it is used extensively. So what are the characteristics, basic characteristics which influence the casting quality? It is refractoriness of the sand, that is its fusion point, the temperature it can resist. Linear expansion, the sand grain will expand when the metal is poured, and this expansion of sand can cause certain sand defects of the casting, we will discuss shortly. The grain size, shape and distribution will decide the texture of the mold and what will be replicated on the casting surface. The AFS clay content of the sand, the clay content should be as low as possible. The clay will consume binder but will not contribute to the strength. Also, more clay content, the sand will be more compact and expansion characteristics will be hampered. And last is acid demand value, which affects use of certain resin binders. So the acid demand value should be checked when certain resins are to be used. The basic major molding materials or molding sands used are silica sand, zircon, chromite, olivine, and alumina. We will see one by one what are the characteristics of all these sands. We just discussed the expansion characteristics. The silica sands satisfy most of the characteristics fairly, except its expansion characteristics. Silica basically is a quartzite, it's quartz, and its crystallographic it changes at temperatures say 573, 870 and 1470 from alpha to beta, that is cristobalite, and this changes causes the individual grain of silica sand to expand. From this graph you can see expansion of silica sand grains is almost 8 times that of zircon sand, 4 times of chromite sand, and almost double of olivine sand. See, you have rammed the mold. The sand grains are compacted. If the individual grain starts expanding, there is no space for the grain to expand. Then what happens is the sand buckles, it cracks. When it buckles and crack is formed, metal inserts into it and you get scab. The same cracks, when they are formed in corner, heavier sections or inside the core, you get rat tail or veining defects. These are the defects caused by expansion of the sand, and this is where silica sand is inferior to all other sands. Next sand used is zircon sand. It is zirconium silicate. It is excellent sand and meets all the requirements. It is neutral, doesn't react with most of any metal. It has excellent thermal properties, very high fusion point, very low thermal expansion. The sand grains are round in nature. Unfortunately, the cost is very high. This is a byproduct of heavy metal production, that is atomic energy applications, and hence its application is being steadily discouraged for foundry use. Now it is mainly used only in paints or in some proportion to some very high alloy and intricate investment casting slurries. However, zircon sand full molds, it is difficult to make casting that the metal gets chilled and you get a lot of cold shuts. When only zircon sand, it was or it is being used only for chilling purposes, so that sand doesn't fuse in heavy sections of a steel casting. Advantage of zircon sand is you can mix it with silica sand, 50% zircon, 50% silica, something like that, to get effect of both the sands. You can reduce the consumption and you can have some effect of neutral chemical reaction and this thing. But again, this use is restricted to heavier junctions only. Chromite sand is a black angular sand. It is highly refractory, chemically non-reactive, good thermal stability. Its thermal expansion is, though more than zircon, is substantially less. Its chilling properties are very excellent. But problem is this is a mined sand. This is crushed sand. So you get angular, and to get the exact distribution required is difficult. This chromite sand is again used at heavier metal junctions so that the metal doesn't fuse. You have to control the SiO2 and CO2 percentage in this, because when the SiO2 free SiO2 is more, it can react with chromite and iron when the metal is poured and form a solid mass, a hard fuse mass. The next sand is olivine sand. This is also a mined sand. It is green in color, so called olivine. It's magnesite and iron silicate. The physical characteristics, mechanical, chemical characteristics slightly vary depending on the proportions of this. Unfortunately, it is difficult to get exact proportions and exact distribution of sand. It is used mainly for making manganese steel casting, because manganese doesn't react with this Mg and you get a much better surface. However, you have to use calcined after calcination of this sand, because there is serpentine in this sand, and serpentine being hygroscopic absorbs moisture and you can get blowholes in the casting. Aluminium silicate. This is neutral sand. This has all the good qualities. Now you get rounded grains, you can get the distribution you want. However, it is fused and used. It is much costlier. In normal molding processes, normally not used. You can't afford it. However, it is used in making certain investment casting slurries along with zircon. The specific chemical specification of silica sand, it is 98% purity, and mostly you get this purity. However, you should control the TiO2, CaO in this, and also the clay percent and moisture. This is specification of chromite sand. The chromite is around 45 to 50%. Iron is very high. You have to control the SiO2 percent. Now the specification mentions less than 1%. It is difficult to get 1%. But if it goes more than 3 to 4%, you will probably end up with problems. So you should check that. Also, the distribution you should check. You may not get the exact distribution you want. This is mostly imported sand, but still used in heavier section in steel casting for chilling and where fusion of sand is expected. However, if this is used in high proportion and a reclaimed sand is used for facing, this can create issues again of reaction of chromite and silica. This is a photograph of the chromite sand used and fused at a heavier junction because of reaction with silica and iron. This is called double sand effect or elephant skin defect, and this then can be removed only by chipping. Even by grinding it is difficult because it is a hard refractory mass and doesn't get ground. Fettling becomes a major issue if this sand layer is formed. Is use of olivine sand. Olivine sand is used in Hatfield steel. Also, you should check the chemical composition, and if FeO content, CaO content are higher, you should check on it. MgO content as given in the specification is 50%. You should try and see that it is more than 50%. It has high alkali content and it doesn't go well with certain resins. You have to choose the resin sand mixture if you are using it properly. It is only used mainly in manganese steel because silica sand grains react with manganese steel and you get a very bad surface. The grains of this are angular. It is expensive and not available at all the locations in India. The transportation cost adds to it. This also is used after calcination as you want to remove the serpentine portion, which is hygroscopic. This is comparative of molding sands. AFS grain size normally what you get. Silica you can get whatever grain size distribution AFS number you want. Zircon you get much finer. Chromite and olivine also, but chromite and olivine it is difficult to get the 3 or 4 sieve distribution which you normally sought to have proper compaction of the sand grains. You see the thermal expansion of silica sand is for more than 4 times of zircon, 3 times of chromite, and again the silica sand is non-linear. The refractoriness also is less, but around 1419 1500 with application of paint, silica satisfied most of the requirements of sand and can be used effectively. The basic grain structure shape, it contributes a lot about the properties of molding sand. You seek a rounded grain, so the binder required are less because the surface to volume ratio of a sphere is less compared to all other shapes. However, it is difficult to get exact spherical. In practical, what you can subangular rounded and medium sphericity. At the sand surface increases, I mean, if you don't have rounded grains, the bonding material increases. The rounded grains also have better flowability, better permeability. The porosity of the mold controls the permeability. When the grains are compacted, rounded grains will leave certain voids, provided you have proper distribution of sand. You try and procure sand between 3 or 4 safe distribution, it is 80%, so that there are no much fines and the gap between the two grains is not filled by the fines. You get good permeability. This size distribution is designated by AFS number, which is weighted average of different grains, and the specification of sand you can have, say you want 50 60 AFS or 70 AFS which is much finer, or 45 AFS which is coarser. The clay content or fines are normally quoted as 0.5 or 1%, which you get in wash sands, and spread you mentioned 3 sieve distribution 70 to 80%. From the sand grains you make a sand mixture with which you make a mold. The grains are mixed with ingredients, binders, so that can be bound together when rammed, compacted or heated. And the formed mold should retain its shelf. From general viewpoint, the sand should be readily moldable and produce defective casting if it is used. Certain specific properties has been identified: green, dry, hot compression and retain strength of a sand mixture. Green strength is strength of a mixture in green stage. This is applicable mainly to green sand. Dry sand is after the mold has been dried. Hot compression strength is hot strength of a mixture. This is required to be high so that the sand doesn't get eroded when the metal is flowing through it and it retains its shape. Retained strength is the strength of a sand after the metal has been poured and when it is cooling. The retained strength should be as low as possible so that the casting cools. The contraction takes place without any hindrance and you don't get hot tears and cracks. Second most important property is moisture of the mixture, which is also again mainly applicable to green sands. Permeability, it is applicable to all the sands. Permeability decides the gases which can go through without producing blowholes. Flowability sand is good. Flowability is required so that molding is easier. Sand gets compacted into intricate shapes. Refractoriness is again important so that the sand doesn't get fused. Collapsibility is low retain strength so that decoring and casting contraction is not hindered. So it should produce a good surface finish. It should have good mold hardness. It should not deform. These are requirement of a mold so that sand erosion and sand shape of the casting is maintained. Sand is reusable, so it is reclaimable and can be used again and again. And is heat removal from the, heat transmission from the casting should be good. These are the properties we seek from the sand mixer we are using. So what are the different sand mixes we use? Green sand. This is the basic sand age-old technique where bentonite clay is mixed with the sand with some water. The clay develops a layer on the grain. The grains are when rammed, formed together, and some strength is, though the strength is very low, this is a very fast process of molding. Since no gassing is required like CO2 process or not waiting for the self-hardening process, it is cheapest process. It is most convenient for machine molding applications like jolting, squeezing, ramming, or Harman machines, or slant slingers, or turntables, because it is very fast. You can ram the sand and the mold can be stripped. The mold is ready. Dry sand was used earlier, in which the same sand, some small amount of core oil and fire clay and iron oxide was used, but I think probably nobody is using because Novec and CO2 sands have become quite common now. But green sand has its own advantages. Its collapsibility is very good and still used by many foundries, especially where machine molding is used or very small casting, not very stringent requirements are to be made. It can be comfortably painted with spray painting, and you get a fairly good surface finish as well. Second most common use is self-hardening process, that is resin self-set process. Here again the hot and cold two processes are there. Hot resins are shell molding or hot box, and cold moses there is a number of things, different combinations. The resin and catalyst are mixed and coated on a sand grains, normally on a continuous mixer. The sand is dropped on a molding box where pattern is kept and it is rammed. As soon as you coat the sand with resin and catalyst, the reaction starts and the sand starts getting setting. However, you have to make the mold before the sand gets set so that you are able to ram the sand properly. This is called work time or bench life of the sand of Novec sand. Then again, you cannot strip the pattern immediately, as sand has to develop sufficient strength to retain the shape. So the setting time is called strip time. The work time and strip time of the sand can be changed depending on the which catalyst you are using, or changing the addition of the catalyst, like fast setting, slow setting, quantity. Supposing a batch, small jobbing foundry is there which makes from 500 kg to 5 ton casting, the molding box size will vary, the time required to make mold is vary, and these all variations in sand properties are required. But most of the current sand mixers, continuous mixers used, have these facilities and can be used conveniently. The major disadvantage of this process is the gas generation and cost. The gas generation when the resin burns is substantially high, and that's why you get pitting of this gas when it is generated. You have to take proper care with applying proper coating and having sufficient permeability or venting of the mold so that the gas doesn't come inside the casting. The third more important molding mixture used is CO2 sand, where the sand is mixed with sodium silicate and CO2 gas is passed, whereby a silica gel is formed, which subsequently gets hardened. This is also an excellent sand. In fact, it has got all the advantages of a Novec sand, much cheaper. Two disadvantages is the gassing time required and The major disadvantage is retained strength. Its retained strength is very high, and probability of casting getting crack and decoring both are disadvantages. However, at around 500 to 600 degrees centigrade, the CO2 sand mixture form a meshy zone, which is not very hard. If your sand is not going to reach the temperature from the configuration of the casting beyond 500 or 600, you can use CO2 sand without any problems of collapsibility, and you can have saving also in this. However, reclamation of CO2 sand is very difficult. CO2 sand can be completely reclaimed only by wet process, that is washing of the sand, which is now practically impossible with the quantity of water required. These are so many differences of resins and pre-squared types of use. These are all basically resin sands. For the surface finish, the basic problem starts when the metal is poured in the mold. What will happen in the normal course? Normal course, when the metal is poured in the, it should take shape of the sand grains. So if the sand grains are very fine, you should get a fine texture. If the sand grains are coarse, you should get slightly coarse, and it should stop there. But two things happen when the metal is poured in the mold. When the metal is poured and with the hydrostatic pressure, or because of the high fluidity at these temperatures, it goes into the pores between the two sand grains. The sand grain between the metal gets fused because at that temperature it doesn't retain its thermal characteristics, and you get a fused layer of sand on the surface. To avoid this, what you will try and do is have a coating of refractory material which will close the pores. The refractory material have substantially higher refractoriness. It is less reactive with the metal, and you try and get a better surface finish. This is the basic requirement of a coating. So it should be a barrier between the metal and mold. It should have more thermal, better thermal characteristic, high refractoriness, non-reactiveness, very small size, so that you get a base surface finish. Penetration is mechanically happens. There are also chemical reaction which takes place, which is more dangerous, and this is the major cause of bad surface finish in steel casting. When the steel is poured in a mold, in the process it gets oxidized and FeO is formed. You have deoxidized, taken all the care, but when the metal is poured into the ladle, it gets exposed to the air. Again, when it is transported and poured in the mold, it is again getting exposed to the air, and FeO is formed. The FeO formed has much lower melting point, and at melting temperature of the metal, the fluidity is very high. So it starts reacting with the silica and forms Fe2SiO4, which again has a very low melting point. This doesn't happen in cast iron because the carbon in cast iron itself is high. The FeO basically doesn't get formed. Now we'll come to see when FeO comes in contact with the sand layer, it starts reacting. It first goes between the two sand grains because its fluidity is good. Apart from its fluidity, it starts react with the sand grain and forms Fe2SiO4. These reaction products still have much lower melting point, and at this temperature its fluidity is substantially high. The penetration rate is very high, and you get a very thick layer of sand fused layer. This penetration and this cause the wettability, that is ability of the metal, that FeO and Fe2SiO4 form is substantially higher, we'll see what is wettability. If you drop water on glass and if you drop a water oil on glass, you can see the contact made by oil and contact made by the water. Compare it with the steel ball kept on a glass. The steel ball will have a minimum contact, oil will have more than that, water will have much more. Now you imagine a drop of water on a chalk or sand. It will get sprayed immediately. This is what is wettability and surface tension of a liquid when it is coming in contact with a solid layer. The angle, the wettability angle, the theta, is defined, and this wettability angle of Fe is much less. It is 21 degree, and wettability angle of iron oxide is substantially more. This is the reason you have to choose a proper layer of refractory so that the iron oxide doesn't get formed, doesn't spread very easily, and the reaction doesn't proceed very fast. These are the reactions, and whatever you gave from whether water will have or theta angle and what this. This is all dependent on the basic characteristics of the chemical reaction between metal and mold. This chemical reaction basically is responsible for wetting completely the mold grains, sand grains by the oxides, which causes sand fusion. At the same time, we want, when coating is required, coating is to be applied on the mold, we want the wetting angle of the coating to be excessively high so that spread of coating is very good. The importance of foundry coating in improving surface quality cannot be overemphasized. It depends basically on the characteristics of the paint, and one has to choose the proper coating material. So what are the important characteristics of the coating material? We'll see. A refractory coating should, the refractory, basic refractory, which should have a high fusion point. See, we are trying to give a coating of refractory fines on the mold surface, but the dry refractory cannot be coated, so it has to be carried through some liquid so it can be sprayed or coated properly. Normally, the carriers are either water or alcohol, spirit base. When you are trying to carry it and the refractory is coated, it should remain there and should not be friable and come out. So you need a binding agent to keep the grains bound together. Also, when the paint you are applying, the refractory should remain in suspension in the paint. So you need a suspension agent. So these are the 4 ingredients you need in a coating. The coating should be correctly applied on a sand wall. The refractory material should have high fusion point, low expansion, chemically inert to the metal, sufficient refractory properties to cope with the metal being poured, good adhesion to the substrata. The coating should get adhered, it should not spill out, it should not spat, it should not form cracks, blisters. It should dry fast. Blistering, cracking and scaling should not happen. The mixture should have good suspension. The coarse or mold strength should not degrade. The metal penetration should stop. For all these, the basic agents are, as discussed, refractory filler, liquid carrier, suspension agent, binding agent, and certain additional additives are required so that the spread of the metal or that scaling, cracking, blistering properties are adjusted. So basically, refractory filler, binder and suspension agent, these are added to the liquid carrier and additives are added, and so the coating is ready to be applied to substrata, that is sand or core mold. The refractory material is the base of a coating, which determines how efficient the coating is. Normally, in a refractory coating, the refractory particle constitute 50 to 70%. Its particle size, shape, density, centering point, thermal properties, chemical properties, expansion characteristic, reactivity, etc. They are all considered for deciding exact appropriate coating for a proper application. See, the application may depend on the metal you are pouring and the size of the casting, the surface finish requirement, etc., etc. The different refractory materials use plumbago, silica, graphite, coke, anthracite, zircon, magnesite, olivine, glaze, chrome, alumina, mica, etc., etc. The refractory considers a type of the metal poured, pouring temperature, the thickness of the casting. The heavier casting will need better refractoriness because the sand is going to be heated for a longer time. Peel characteristic. The metal, the coat should not peel off. It should remain stick on the sand or core. Thermal conductivity, expansion characteristics, application characteristics, toxicity. While coating the pond, sometimes there are bad odor or fumes which are coming from the alcohol. That a proper carrier should be choose. It should get applied uniformly. In shipment, it should not settle down, or its bench life should be good, and permeability of the coating. We'll consider what are the different refractory materials normally used in steel casting. The best is as such zircon floor. It has the best of characteristics. As discussed while discussing, sand has good refractoriness, excellent fusion point, very high conductivity, very low expansion. Everything good is there except cost naturally. The zircon has 64% ZrO2 and 32% SiO2, 35% SiO2. You should check the content of TiO2, and it is the moisture in it should be controlled. Its specific gravity, pH values, fusion point, all are good. This is the best coating material available. Now this is used in mixture with some other refractory materials. Second is used olivine. We have seen as olivine has good chemical reactivity with manganese steel, and this is mainly used for manganese steel and some other heavy application. Again, the chemical composition is to be checked properly. Its thermal expansion is slightly lower than silica, but it is not as good as zircon. Fusion point is high, 1800. It is more than silica, but lower than zircon. But this paint is used for manganese steel. This is the comparative data of refractory materials used for painting application. Stamot, chromite, magnesite, chrome magnesite. Availability, refractoriness. You will find that mostly magnesite and zircon only are used. The next ingredient of a coating is carrier, that is either water or alcohol you have used. Water is non-inflammable, non-toxic, naturally cheapest, and use of water-based coatings is highly recommended, but naturally cannot be used on all types of sand. But whenever possible, water-based coating, you should try and use them. The only disadvantage is naturally it cannot be used on all sand, but it has got more chance of dripping and runs forming. Also at very low temperatures, not experienced here in most part of India, but at sub-zero temperature, these coatings can freeze. Next is organic carriers. these are mainly isopropanels, that is alcohol base. The coating has to be dried by igniting or heating. The typical organic solvent carriers also include methanol, ethanol, hydrocarbon, chlorinated hydrocarbon, etc. They dry very fast. Isopropanol is recommended for use on large molds and copper. See, the basic requirement is when you are using a alcohol-based agent, it should burn with a slow heat. The heat generated should not be very high, so that the basic sand binders burn away. Also, if it is air dryable, it is better. Suspension agents. See, you are having a refractory which are very heavy material being carried in water or alcohol. So it is most likely that when you are trying to apply it, it will settle down. The viscosity or bombing of the paint will not be constant. So to keep them in suspension all the time, suspension agents are required so that gravity doesn't try to settle the heavier points. The agent provides suspension system, the filler particles for agglomerating and separating out during stationary coating over the extended period. It's proper, they are required normally 1 to 5%. As we have said, 50 to 70% is refractory only, 1 to 5% is coating, balance is mainly the carrier. Suspension agent should ensure that the homogeneous coat is available most of the time with minor stirring. The primary function is should not allow it to settle in storage and steepment, and should not form a hard layer at bottom. That is, the bench life of the paint when kept in a container should be fairly good. Otherwise, a very hard layer will be formed, and then it will not get mixed with the thinner or alcohol properly. Also, it should be possible to easily apply the coat by brushing, swabbing, or spraying. Special additives, they may include deep foamers, that foaming should not run, wetting agents, biocides, dispensers, and leveling agent. See, the application of actual paint needs this wetting and leveling agent so that you get a uniform coat of the required thickness easily. You should get a uniform thickness coat all over the mold to get a better finish of the casting. Second ingredient is binding agent. You are trying to coat the refractory on the mold. After coating through a carrier, it should remain there bonded together and should not come out. I mean, it should not be friable that it gets washed away with the metal. For water suspension, the binding agents are sulfite light, dextrine, bentonite, kaolin clays, or certain water-soluble resins. For spirit-based suspension, natural synthetic resins, phenol, urea formaldehyde, novalac, and other wood resins are used. Binding various metals which act to hold particles refract together and attach them to sand surface. The quantity of binder is again 1 to 5%. It is important to determine the minimum quantity of the agent required. See, if it is high, the coat will crack. If it is low, it will get washed away. So, for the molds sand system you are using, you have to settle a proper mold coating which gets a uniform coating. You may have to carry out certain trials with different paints, but settle with a paint which gives you exact uniform coat all over the mold. Furthermore, the binders itself should not, when get heated, should not evolve much gases because they are resin based. Now the coating is to be applied on mold, and there are various ways how a coating can be applied. The various ways are brushing or swabbing, spraying, deep coating, or floor coating. We'll see one by one what are the advantages and disadvantages of the different coating material. Brushing or swabbing method are applying coating used in foundries. You have to just brush the paint. You have to ensure that the paint remains in properly stirred and refractory in suspension condition, because For a bigger mold to brush, you will take a lot of time. The disadvantage, you are forcing the force applied while brushing. There is certain force is applied, so there is sufficient force to enforce the small refractory particles into go into pores between the two sand grains. The method gives uneven thickness, and the stripes of brush or swab are visible on the casting surface, especially in wall and other casting where aesthetic values are important. They don't allow these brush stripes or brush marks. So many times after one brush coating, you have to give a fine spray coating so that the brush marks are not seen. You can use 70, 75 or up to 80 Bomi for water base and 60, 70 Bomi for alcohol base. This Bomi can be changed for thicker or smaller casting depending on what surface finish is expected. Next method of applying coating is spraying. Spraying is much faster of application used in foundries. Care you have to take is you get uniform air pressure so that the coat is uniform. You also see that the air you get is completely moisture free. The permeability of the coat is good enough so that the air entrapment is not there. The viscosity of the use for coating is slightly lower than brushing. For water, it is around 50-60 and slightly lower for alcohol base. Again, spraying is problematic where intricate shapes are there. You have to use different angle spray guns for coating those portions, or you may have to brush those areas. Again, the nozzle size through which your paint is being sprayed should be checked intermittently so you get proper thickness of the coat. Green sand molds, it is difficult to brush them because the sand grain strength is not so high, and while brushing, the sand grains will loosen. Also, it may not become uniform. Spraying is preferred. Water-based paint cannot be probably used on green sand because the moisture will increase. It is very difficult to, torch and break only the excessive moisture. Green sand should be used mostly for spray painting of alcohol-based paint, and those paint should be ignited, taking care that they don't accumulate at the bottom portion. Excessive paint is not there, so it will not form gases. It is good adhesion to the mold surface. After spraying, the coating could get ignited, or it could be natural dried. Natural dried is difficult because you will have to give a lot of time. You should ensure that there is no peeling, cracking or blistering of the coating. You have to settle for whatever system of sand and coat you are using with using different coats. Whichever basically gives you a uniform good coating and good surface, you should continue to use that. There are many variables and you have to choose a proper between them. The basically strength of the surface area in green sand or other is slightly improved after the coat is ignited and the hard layer is formed. It should form in a reasonable time. Third process is use deep coating. Deep coating is mainly used for cores. That also when the cores are small and the large production runs are there, so you can standardize the coating thickness which you get. If you dip it, if you withdraw it fast, there is no sufficient time for the paint to drop back into the tank and the thickness will be more. Also, you can get the faster withdrawal speed, the more coating suspension is pulled and the substrata because no time for suspension to flow back into the mold. You should standardize the timing. If it is mechanized completely, it is better. This can be done only where large runs of cores and molds are used. You should also ensure that the viscosity of the paint is maintained in the tank. Also, fungus or other things should not form because many times people just keep on adding paint when it is first level is dropped. You should keep proper place to keep the core after draining. and you should ensure that there are no drippings or runs. While coating, we have to ensure in deep coating that uniform layer is applied. Optimum coating thickness of the coating is there. It depending on your requirement, the metal you are pouring and the thickness of metal around the core or mold. There is no moisture left. There is suspension in the tank and resistant to bacteria formation is good. Satisfactory bond strength, suitable rheology and application. Rheology is suspension only and application characteristics. When you coat the paint or dip, firstly you get a glossy surface, and after the paint is completely either slightly absorbed in the coating or gets dropped, you get a matte finish. What you are trying is for a matte finish and not a glossy surface. Glossy surface is likely to peel off if it remains glossy and thick coat like that. Longer matte time, the time from glass to matte. The longer matte time is good for brushing applications. Shorter matte time is good for coating dips or runs to avoid. Last process is flooding. In flooding, actually a normal garden hose without any pressure or normal hydraulic pump pressure is used. It is used for very heavy and odd molds. You have to have the mechanical arrangement to hold the mold tilted, and also mechanical arrangement to collect the paint which drops in the tank, again filter it and again reuse it. Basically suitable mainly for water-based paints on no-bake large molds. It can be also used for cores, but it is better that the cores are on a turntable, they move continuously, so the coating doesn't get spread properly, there are no runs and drippings. It should be, as said, 30 to 40 degree angle so that it drops properly, but it gives thick uniform coating and water-based coating, and it's substantially faster. If such a big mold you have to paint by brush and thing, you will take a very large time. Also the transfer efficiency. I mean, if there is certain quantity of refractory in the coating and you check after the coating is applied how much refractory is actually goes into mold or core coat, by flow coating is its maximum because it is very fast and you can have whatever thickness of coating other than spraying or dipping. The process has to be standardized, but mainly used for very heavy molds, normally not used for smaller molds. After the coating is applied, the question comes for drying. After coat should be dried properly, suspension agent completely removed. The substance do penetrate mold and core material, but ensure that it doesn't affect the core and mold original strength of the hand. It doesn't become friable. The gas formation, slag entrapment, etc. do not happen. The organic based carriers, they get slightly heated and burned properly. The problem only comes mainly with water-based paint coating. For drying water-based paint, mainly you can have ovens. I mean, ovens. Normally, a hood or bogie is kept where molds are made, and molds are made to travel through that. So it is continuously there, or it is left when the large molds are there. They are left overnight for next day. Still, it may not get completely dry. So you have to use microwave or drying tunnels or high intensity lights. Torching should be judiciously used. What happens in torching? It is manually controlled. The heat applied may be very high. Apart from drying the coating, it may burn the resin or the binder of the sand and make it friable. So the drying should be at a predetermined time. If you are drying it on a oven or floor, the important characteristics of a coating are specific gravity, is the refractory content Basically, it is refractory content in the paint. The higher the refractory content, the specific gravity will be more. It can be measured, but not very easy to be measured. Penetration depth. When you are applying a paint, to what depth it has penetrated in the core or mold surface. It should be, you cannot say it is more or less, it is the required depth to give you a better surface finish. For a higher thickness of metal, you should have a better thickness, better penetration. For a smaller made, you can have a smaller metal thickness. Viscosity is measured by flowing through a cup, standard cup. Paint is taken in the one standard cup and paint is allowed to flow through it. A stopwatch is used and the time taken for the paint to completely run out of this cup is taken. It's a arbitrary number. You have to ensure whatever paint you are standardized using, you have to intermittently check the use of it and ensure that the viscosity of the paint is properly maintained, so you are getting the required thickness of the coat. The most other practical test is BOMI, where it is a glass tube with a bulb at the bottom, which is filled with either lead balls. It suspends in a liquid. When kept in a liquid, depending on the viscosity of the liquid, it will dip into it, and the mark on the BOMI, what you talked earlier, that water-based paint can be of 70 BOMI or alcohol-based paint can be of 65 BOMI for brush painting. This BOMI number is from the standard BOMI meter. When it is immersed in a liquid, at what level it settles, that marking on the tube should be 65 or 70. For checking thickness of the paint, when you have done all this, how to check the thickness, whether it has correctly applied it. There is a standard label all this. It is difficult to check the paint thickness after it is dried. So wet paint is checked with this. There are depth on this at various level, and to what depth paint is there, that is measured and standardized for your application. There is a ASTM standard for this application. Normally, as a thumb rule, the dry coating thickness is half the wet coat. The coating permeability is important for two things. When you are spraying it, some air also gets entrapped. It should be able to go for the air to go out, and when the films dried, the gases generated should be able to go out. The permeability of the coating, there is a measure, permemeter, used for measuring this permeability of this coating. Wettability and surface tension. As we discussed earlier, comparing a steel ball, oil drop or water drop, the wettability of the coating should be as high and as good, so that it spreads very fast and you can give a uniform coating to the mold and core very easily. Dry coatings normally in steel casting not applied, but very small casting you can use. Some people use chalk stick or mica or some powders, floors or quartzite powder to just kept in a cloth, and it is coating is given on the mold. Normally it is used for cast iron smaller casting, where graphite or amorphous carbon graphite is crystalline graphite plumbago is kept in a cloth and spread. Normally not used on steel castings. Full mold casting or quite a few casting, large casting especially, one-time requirement are nowadays made with full mold process. The coating requirement are somewhat different, but much more important in this case. See, when you are pouring in lost foam process, the foam pattern is coated first. The mold is not coated. It is coated by 1 or 2 coating, dried completely outside or in sun ray or using infrared rays. It is molded, and when you are pouring, the gas, substantial amount of gas is formed when the foam burns. The gas formed by the cone should pass through this coat. There is no other way for the gas to go. When the gas forms at the lower temperature through the coating, the lustrous carbon is not formed. Liquid is not formed film. And you don't get the liquid carbon on the casting surface, which gives bad surface in full mold casting. These specialized coatings are developed by various people, mainly by Foseco and other people. You have to avoid the liquid pyrolysis product, which is a carbon film, liquid carbon film or tar accumulating. For this to stop, gas formed should pass through as fast as possible. That's why the permeability of this coat becomes very important in this case. This is to get the basic surface finish of the casting. The surface finish also depending on your finishing operation, the way you are cutting, the way you are grinding, the way you are finishing, short blasting, etc. You have to ensure that the cutting marks of either electrode cutting or gas cutting are not deep and left. You should grind the riser or runner portion properly. If there is upgradation, that also portion should be ground. It should be ground smooth so that the surface is not. But what happens is whenever you ground these portions of riser, pads or upgradation, the natural texture of the sand of the casting gets disturbed, which many people have objection when they are specifically looking for aesthetic view. To some extent, not 100%, but can be made by excessive short blasting of these surfaces. You have to use specific hard balls of bigger size and short blast this casting, so some amount of texturing, natural texturing is restored. See, there are so many different applications nowadays coming apart from normal casting, which are, casting which are subsequently machined, the surface finish requirement doesn't come so much importance because the surface is as much going to be machined. Where it is not going to machine and used directly, and when it is going to be seen by people, the aesthetic value comes in the picture. That's why it's more important in pumps and valves, because they form part of a bigger equipment where other parts are better. I can give an example of, we have recently completed one steel casting big order. This was for Andaman Nicobar Airport. See, this is something which has come out of the brain by architecture, certain designs. And he decides to use casting in some application. The balance is all pipes or steel. He gets a uniform surface on the pipes and other structure. He wants that uniformity on a casting, which is very difficult to get. But a lot of application on this case where it becomes important to get this finish, so that importance of sand and coatings. Thank you. I think I have finished. So if any questions are there.
Yeah, there are a few questions. I will read it out. Mr. Arun Ranganathan is asking zircon floor used for coating. What mesh size is suitable for that?
What mesh?
Yeah.
Normally minus 200, minus 270 used, but these are proprietary of the paint manufacturer. Normally we don't come into picture of all this.
Okay.
We have to decide, you try some paint If it is giving good performance, stick to it. Keep on checking the properties by body or viscosity or whatever properties you can check comfortably.
One more question is that if the collapsible agent is to be used, what kind of collapsible agent and what is the recommended percentage?
This is in CO2 sand, he is asking.
Yeah, in CO2 sand.
Normally 0.5% Dexil is used. They are starch dextrin based, I mean starch based. You can use plain dextrin 0.5 to 1%. It is again depend on what collapsibility you want. Normally 0.5% dextrin is used. Dexil, I mean the proprietary name of Poseco is Dexil. I mean I should not use some name of some proprietary names, but these are popular names. Yeah, they are equivalent grades by all manufacturers. Normally 0.5% is used. You can use wood floor also. This is very cheap. See, wood floor you use, it will burn and create some voids. But the gas evaluation, it should not happen. It is going to evolve some gases.
And if in case of CO2 molding, how long a mold can be kept?
Practically, there is no. We have used CO2 mold after strike after 3.5 months. Nothing happens. Provided it has not picked up moisture. It depends more on season. If it is a rainy season, it may be difficult to predict the time. It may be very less. You will have to dry it by torching before you actually using it. Say the CO2 reaction is reversible. If the moisture is absent, the silica cell can get reversed. So it will again depend mainly on the atmosphere. That if it is rainy season, you will have problem. It is a dry season, there is practically no limitation.
One question regarding olivine sand: to what temperature and for how long should olivine sand be heated to get rid of serpentine? Is the same applicable for chromite sands also?
Yeah, they are normally calcined at around 900 degrees centigrade. But they are calcined at very raw process. I don't think they check that temperature, etc. very. And that is why, that is the problem of using olivine sand. One thing is availability. It is in south at certain portions it is available. It is not available randomly. Many times the transport cost becomes much more than the actual cost of sand. As such, it is costly. I think it may be something around 7,000 rupees a ton today.
I think there are no more questions in the either question answer or chat box.
Okay.
So thank you, sir, for your excellent lecture. I request Mr. Shyam Arjunwadkar to offer his comments and vote of thanks.
Mr. Panse, very much thankful to you. It's a very thoughtful lecture. What we are
listening. For giving me opportunity to speak in this forum.
No, it's our pleasure. It's our pleasure.
Okay.
You have started from basics of the sand, selection of the sands to the selection of the coating to the blending, what it goes into the making of a coating, and how to make the application of it. Not only application, but what are the practical tips to select the thing. And
actually, this is a very wide subject. You can talk only on sand for a full structure. You can
absolutely.
talk.
Absolutely.
I mean, that's what happens here.
What you have talked today. This is what exactly the practicing pottery engineer needs to understand. Because he doesn't have the time to go into the details of it. But for his practicing, he needs this much information, which is enough for him to carry out his activities more confidently. Otherwise, what he would have.
Yeah.
So this is very appropriately told. Well, a couple of things what I will like to say that about the CO2 sand reclamation. Now there are the manufacturers available in India. They
are claiming. They are claiming.
Yeah.
And it gills, not that it doesn't remain, but if you see the basic coating which gets on the grain can be completely removed only by wet application. You are rubbing it. What happened? You are rubbing it. You are rubbing it.
Yeah, no, not only rubbing, but they have devised some systems. I have seen and visited a couple of plants.
Okay.
And nearly 80%, around 75-80% sands could be used again. So that I have seen. So those
actually
that is in the progress. Sir, what I mean is that is a progressive thing.
What a difficulty I said, it is not something impossible. It is much easier to reclaim green sand
Absolutely, absolutely. That is true.
It is not so easy to reclaim
Right.
CO2 sand.
Even the Nobex sands and the resin coated sands are very comfortable to reclaim.
Yeah, Nobek also gets reclaimed. To a large extent, it gets reclaimed. And you have option of thermal reclamation if the availability is there, where the sand becomes as good as new one.
As good as new,
Better than new one because the sand grains are more rounded.
Right. And secondly, I think you have said about the CO2 silicate sand, if you could break down the mold at around 700 or something like that at temperature, then that may be possible. The breakdown of the mold may be convenient and easy.
It's not
my opinion, I think that if you below up to 450, the dimensions are not stabilized.
No. It is not. I'm breakdown. See, the silica gel, it gets hardened and forms glass at around 900.
Yeah.
It becomes stone.
Right.
At around 5 to 600 degrees, it is slightly meshy.
Okay, so you take advantage of that because
if you are able to, you see, there are very thin castings. Sometimes the sand doesn't reach that temperature. So unnecessarily, not necessarily to go for Novec.
Yeah.
The cost difference is substantial in CO2 and Novec.
Right.
So if you can take that judgment and use CO2 sand, it has got its own advantage. See, many times Novec gives more problem because of pitting, the gas evaluation.
Yeah.
Even many times shell molding, smaller casting, especially stainless steel casting, you have to search for low nitrogen resins,
right,
which are again costly.
I mean, this kind of information is very much needed for the practicing person.
Yeah, I mean, so I'm a practical man, so I'm a practical thing.
Yeah. And one more thing, that's my comment that viscosity plays a very important role in your paint coatings and all. The reason is that also you can standardize on your energy consumption, because if the viscosity is maintained properly, your cold drying cost or energy cost for the cold drying, that also remains in that range, desired range what you can see. So in every aspect for the mold drying, cold drying, and the viscosity, they got everything has got the relationship. And as I said, it has got the before cup and all. Those are empirical things. What suits to your shop or what suits to your application, you have to standardize on that, and you have to check from time to time at the suitable.
Most of the jobbing foundries, steel foundries, what happens is people rarely check all these things.
Yeah. But I will recommend, I agree with you, I recommend that at least with the before cup, they should check the viscosity intermittently. Even if
it is very easy to check. You check simple. Your bumpy at least.
Yeah, so simple. So simple you can do that. Yeah. Well, I'm really happy. I'm sure that there will be calls after this lecture to get the presentation or get the recording of this thing as usual, because
I already sent. PPT already sent.
Yeah, certainly. So I'm just complimenting that. The one thing what I will like to share with the audience is that at NCTS we have prepared 2 products on the today's subject. One is Novec technology for casting, binder system and molding equipment and all. That gives a very elaborately all the types and processes of Novec applications. So whatever Mr. Panse has said today, if you refer to these DVDs, it will be very complementary if you can define your own logic for your shopware application. Similarly, the other DVD is that refractory coating for ferrous and non-ferrous applications. This is also very extensive. Almost all kinds of systems refractory coating are elaborately explained. And what Mr. Panse has told us today, those all phenomena are very well given. Their comparison tables are there, and all detailed information is there. So after this lecture, if you could get this DVDs and then refer to them, and then it will give an exact, rather it will fulfill your exact requirement of your shop floor practice for your own casting, whatever you are making. I think with these couple of additions, what I suggest, I'm really happy to propose very hearty vote of thanks to Mr. Panse.
Thank you.
Our call. And then NCT is very proud of its panel of experts, and Mr. Panse is one of them. So, gentlemen, I'm again thankful to all of you that you have rejoined for this lecture. I look forward every Tuesday. You will be joining us for such for the lectures of your interest. And again, thanks to our director, Mr. Soni, and all the agencies involved into organizing all the technicalities of this lecture. Well, with this, a big thank to all.
Okay, thank you.
Thank
Thank
you.
you very much.
Thank you.
Thank you.